Chris Dale is my name. I'm actually Norwegian, although it might sound like I'm from somewhere else. I work as a penetration tester, incident response for net security. I manage those teams and have some of my staff in the audience as well. I'm also an instructor for SAMS, so I just came back from Dubai, and my throat is actually roasted right now from speaking for 6 days straight. So I might need to have some water during my talk. And I like how my water, listen to the sounds of me swallowing it. It's always so awkward, isn't it? So my talk, a bit pushed on time maybe, but I'm sure we'll be fine. It's not going to be a PowerPoint. It's just going to be demos, actually, because why not? What could go wrong, right? I mean, only demos, that never fails. If something do fail, don't worry about me, all right? So don't feel embarrassed about me feeling that something went wrong. I normally don't, so I want everything to work, of course, but I'm actually intrigued when something fails. I'm like, wow, what just happened? Let's go debug. So just appreciate that and don't feel embarrassed for me. So in this talk, we're actually going to go through a couple of things. First of all, we're going to go through some login failures or attacks against the login procedure. We're going to look at some side channel attacks on timing. Specifically from actually implementing, for example, bcrypt or scrypt or pbkdf2, we might actually inadvertently introduce vulnerabilities in our systems. We're then going to go through how we break into most systems in pen test, very common vulnerability made possible from password spraying. And then we're going to get into command injection, how we can discover these flaws even though they are blind, and how we can utilize them to the fullest, basically causing reverse shells coming back to our systems. So that's going to be fun, hopefully. And then finally, of my talk, I'm going to go through blind SQL injection. So to see how we can actually pull out data from systems, even though there is actually no output coming from an application. There is, most of the time, some kind of output. So for this demo, I have a solution running. Some might have seen this before, but it's basically a simple login page. So most companies have a multitude of these login pages. They probably have like 10, 15. Even if you're a small company, you have a bunch of login pages throughout your environment. And in this dummy login page here, we actually have a vulnerability that is called username enumeration. So when I try to log in as admin, which is, by the way, my default, I try it everywhere, and so should you. I mean, you might get a police report on you for doing this. Who knows? Like, some people are crazy. But this will actually just get you in sometimes. But yeah, you know it's happened. Actually, so for login pages, I always go for admin, and I also search for, in a search field, I search for star or percentage to just see if everything dumps. And very often, yep, you do actually get successful. In this case, though, we do have a vulnerability of a username enumeration vulnerability, right? So we can see that the admin account does not exist, whereas if we did not have a vulnerability, we would have a different error message. For a user that does exist in the database, you can see that login failed, check your password. So this is very, I wouldn't say very common, but very basics. And we want to patch this because we don't want to reveal which users are in our database or not. Like, this should be something of a secret, sort of. So the developer, no clue who that is. It might be me. I'm actually running off the damn vulnerable web application back here. So that's the back end. I have modified it quite a bit. And the developer, me, has now fixed the issue. So if I now log in with admin, you'll see that, hey, there is actually a consistent error message. Login failed. Doesn't say if the user exists. Doesn't say if it's a wrong password, correct username, whatsoever. So this is now hopefully fixed. However, as the developer fixed this issue, he also fixed the password storage of the application. So originally, the password storage was using MD5. Now that's not good enough, right? So we should, of course, use salted MD5. Well, not really. SHA-1, some of you might think, no, Google, they told us that we've broken SHA-1. There's collisions with SHA-1. All right, so SHA-512. No. Passwords should not be stored using hashing mechanisms alone. We should be storing passwords in a password algorithm. We should be using a password algorithm in storing passwords, such as, for example, scrypt, bcrypt, or pbkdf2. These are expensive algorithms that takes time when calculating someone's password. So say, for example, I have a fixed cost of calculating someone's password of 10, and having 10 costs on my server might take password calculation, for example, 500 milliseconds to actually calculate someone's password hash. So you want this hash of someone's password to actually take time and be costly. And hashing algorithms such as, for example, SHA-1, SHA-512, and so on, they're actually made for speed. They're designed to be really, really fast. And we want the password algorithm to be slow. So this actually could cause a vulnerability. So let us try to log in with the solution again, and let us intercept the request in a tool called the burp proxy. So hopefully a lot of you are familiar with this tool already, but this is just a local proxy running on my system that will allow me to intercept the requests. So I'm now going to intercept the login request, and it's immediately being caught by my by my burp suit. And from here, I'm going to actually send this request to a tool called the intruder, which is a fuzzing tool. It allows me to define different variables of the login request. For example, here, I can specify that the admin username, so this is actually the request I sent to the web server before, but here I'm specifying that the admin username is going to be a variable. So I'm going to be fuzzing this variable with values that I control. What type of values do I want to send? Well, potential usernames. I want to see if this username enumeration vulnerability still exists, even though it just says login failed. So where can I get a list of potential usernames against a target platform? Potential usernames. LinkedIn. Perfect place to go. So we have a script at NetSecurity. It basically browses to LinkedIn, searches a company name, and then extracts every single employee from that company and creates potential usernames for that company. So say, for example, if I do a whois lookup now for the domain netsecurity.no, I will see that the owner of the company is john@netsecurity.no. That's a contact address for anyone inquiring information about our domain. So Jan@netsecurity.no, so that's actually Jan Sørgaard. And his username for many of his services is definitely going to be Jan@netsecurity.no. So just from LinkedIn, I can create a little list of potential usernames like this. So here I have, from LinkedIn, just created a list of potential usernames. And by running this attack, first of all, I need to configure my attack. No URL encoding. I'm actually inside of post request here. I'm going to configure the number of threads to just be 1. And I'm going to go all the way down to the bottom here. And I'm going to tell my solution to process cookies in redirections and also to follow redirections. Now, because we have fixed the username enumeration issue, we can see that the content length of each request over here is actually equal. They're identical. Whereas in the old solution, where the error message actually showed me that my username was wrong, I would have a pattern here that I could filter on. I could say that, hey, every time I have a content length of so-and-so value, it means that the username did not exist, whereas a consistent reply from a certain content length would mean that, hey, this user exists, you just got the password wrong. But because we have patched the solution, the content lengths are equal. In every single response here, you will see that it just says that username, login failed, user does not exist, login failed. So no extra information if the user exists or not. But I said I also added bcrypt to this login form. I added some cost of calculating people's passwords. So why don't we take a look at the timings of these requests? And just by looking at them, it might not be like evident. It might not be too obvious. But there is actually some very subtle discrepancies here. Some of the users have about 200 extra milliseconds per request taken, whereas others are 200 milliseconds slower. So Magnus, Jan, and so on, for some reason, they're taking more time than others. And this is actually the vulnerability manifesting again because we implemented a new security measure. Look at all of these requests having about 2,700 milliseconds time taken, 2,600 and so on, versus all of these down here with 2,200, 2,300 and so on. This little line here represents who exists and who does not exist. Avin exists in the system because of this time taken, whereas IDA does not exist because the request was actually more rapid in its response. Now, very subtle issue, but very much real today. I can now, for example, if I was unsure, by the way, if I was not certain, maybe there was a network congestion, some lag, for example, I could just right-click the ones I have and tell my request to, hey, request this again. Where is it? Somewhere. Request item again. And I can now additionally measure the time one more time to just make sure that these requests are actually taking more time than other requests. So just by this, I could now copy all of these usernames, and I could potentially use them in an attack to see if some of them have a weak password. Does any public solutions like this, like very popular solutions like this, exist today, which have the exact same vulnerability? There is. Microsoft, for example, with their Skype for Business solution, they have this exact same vulnerability where you can actually use timing attacks to determine if there exists a certain domain and if there exists certain users within that domain. We use this in every single pen test that we do, because in every single pen test, there's always one or two users who pick a poor password, or where the service desk has picked a poor password for them. So why don't we take these users now, and we can attack them? First of all, by the way, why does this happen? Can you imagine why, like in the source code? Think about it for a second. We're selecting in our database to see if a username exists or not. This is somewhat rapid. I'm running off a Microsoft server here, so it's quite slow actually, but it takes about 2.4 seconds. Now, only when a user exists do we need to check the password. Only when the user exists do we need to check the password. So if a user exists, we will then calculate the bcrypt hash of that user, and bcrypt will take time. It will have some cost to it. Hence, we can determine that, hey, yes, this user actually exists in the database. So the fix would also be quite evident as well, because you could then, for every single request, even if the user does not exist, you will calculate a random hash for bcrypt, for example, adding this cost intentionally to every request. So now let's take these users. Let's take these users and actually attack them. So in our payload section here, I'm going to clear out the previous ones I had, and I'm just going to use the ones that actually exist, the ones we found. 19 users-ish that we know now probably that are actually inside of the system. They're stored in the database. And we reconfigure our attack. We now say that, hey, we're going to use both the password and the username field as variables in our next attack. We're going to use a type of cluster bomb attack. And that sounds really fancy, doesn't it? Like, wow, like this is warfare? Well, it's just a double for loop. So for every username, we're going to try a certain password. That's basically what I'm going to configure right now. So in our payload section here, I'm going to configure up a list of potential passwords. Now these passwords are going to be stupid. NetSecurity123, summer 2016, Vålerenga forever. Very common thing for users to do is pick a password, either I love something or something forever. And also password123 and so on. You might see these things inside of your environments, but what we see the most is the name of the company, and the password is 123. So we're going to adjust our number of threads, and we're just going to hit start attack to see if we can actually see if any users have a weak password. Now you might be thinking, Chris, I'm going to block you. I'm going to block you if you do this to my environment. And yes, you might block me for sure. Be careful what you block though. If you block the IP address, you might inadvertently block your customers actually just having failed logins attempt every morning. For example, if your customer is using a single IP address to access your solutions, you might actually be blocking someone real. Also, you might say that I'm going to block your user account. I'm going to lock it out. And that's a good idea as well. However, it might actually cause people to control when your solution is up and running and when it's down. Like I might cause a denial of service attack against your solution. So looking at this solution right now, there are some discrepancies here. If you filter on content length, let's see, here we have a content length. We can see that there are some funny things happening here. Oh, actually, our attack is actually bugged out. Let's look at the target here. You see this session here? Not a good idea to have this session. We should remove the session because we want the web server to, for every request we make, we don't want it to know that we're actually the same guys. So let's remove the session here and start the attack again. And holy crap, it's just so slow running on Windows sometimes. But let's try one more time. And we should see that the length here is actually very much consistent. And it's actually running faster now that we don't have the session as well. So right now, we're trying to log in with these usernames in the left column. All of these usernames are now being tested to see if anyone have the password netsecurity123. And of course, none of them don't. But all of a sudden, there's a discrepancy. There's something different from my requests. The attackers, they don't know exactly what they're looking for, but I'm just sorting on the number of characters the web server is returning to me. And all of a sudden, I have one request having 2,691 bytes returning instead of the default of 1450. And the attacker, he asks himself, why? He doesn't know necessarily that he caused something to happen. He just goes, why? He goes digging. He's curious. And if you go to the render tab here, we can actually see that it says, greetings, Trondheim Security. We logged in with someone. So just using this blind technique on the usernames, we could figure out which users in the database, and we could find potentially someone who has a weak password. Now this is what happens in most organizations. The attacker gets 1 foot inside of the organization. However, most companies, when they hire people like me, they tell us to pen test outside. So the outside of the organizations are, in many cases, quite hardened. They've been tested before, they've been vulnerability scanned, and so on. However, once you get in here, oh, wow, it's just so nice and cozy for an attacker, because these things here are vulnerable. Like, this is where the vulnerabilities exist. In almost every single pen test, once we have 1 foot inside of the environment, it's game over. This is where we find SQL injections. This is where we find the nasty cross-site scriptings, and so on. So you can just imagine, the attack surface just grew from, maybe we had 10 login fields. And all of a sudden, you get 1 successful login. The attack surface grew to like this phenomenal, huge place for us to have fun in. Of course, the customer should pay for having this tested now. So let's look at some of the functionality. Here we can tickle a server. We can see if we have some reachable equipment. So apparently, this is some kind of hosting stuff or whatever it is. We have some equipment connected. And we can input into the application some of these values in the list. And while inputting, it just says, hey, equipment is connected. Cool. And notice, it took a few seconds as well. So that might give a clue what is actually running in the back end here. But it says equipment is connected. As an attacker, we might ask ourselves, look, I have a list of different equipment. Can I try something else here? Can I like try localhost? Can I see if localhost is connected to this server, this infrastructure? We're curious. We're asking questions, and we're trying. So trying against localhost, it also says, hey, equipment is connected. What about Google? Can I see if Google is connected? And for every request here, it takes a few seconds, but then it says, could not reach, failed with status 1. Huh. So it does not go to Google. Actually, this server is offline for the moment, so it can't reach Google. But we might be curious, what is happening here? So why don't we fire up a Linux VM, such as Kali Linux, and we're going to bring over TCP dump. We're going to listen on Ethernet 0 non-promiscuously. So we're just going to capture packets destined for our interface. And we're going to look for traffic coming from our target web server. The target that we're attacking, we're just going to see if we can get any traffic from that target to come to us. So I'm going to fire up TCP dump. Thank you. Someone is paying attention. Good. So we're now listening for some ARPs. That's all good and stuff, good and fun. And let's input the IP address of our Linux here, which is 192.168.56.50. So can we check if the attacker's IP address is up? We click submit, and it says equipment is connected. Cool. The attacker is online. However, in the background here, in TCP dump, in the packets that actually flows throughout our network, we can see ICMP echo request and replies. In fact, we can see 2 of them. 2 requests and 2 replies. So this gives us indications of what the application is doing. They're just pinging something to see if it's up or not. Pretty cool. What else? So with a command injection vulnerability, we're asking ourselves, what else could we potentially do with this IP address here and this command? Could we, for example, inject other stuff inside of this command? Like maybe tell it to only ping once. So we click -N1 and click submit, and we only get 1 ping coming into our solution. All right, cool. So we can add parameters to this command. Ooh. In fact, what a lot of vulnerability scanners are doing, so such as Nessus, such as burpsuite, such as many others, they're just adding, hey, ping this solution 15 times, and they're going to add localhost here. So they're going to say ping localhost 15 times. This is their injection. This is how they try to determine if something is vulnerability, something has a vulnerability or not. And they're just looking at the solution, and all of a sudden, it takes 15 extra seconds to run. Yeah, each ping normally takes 1 second. So they just measure the time from a normal request, which takes about 2 seconds in my slow system, and all of a sudden, they inject this dash N15, or for Linux, dash C15, and it takes 15 seconds to run. And they go, ha, command injection. Cool. So we might have a vulnerability here, but what else can we do? Like, can we maybe append any commands here? Can we add any commands? Can we do something more here? Potentially. How do we, for example, append commands on Linux? Semicolon is not correct, sorry. Oh, on Linux, yeah, my bad. On Windows, thank you, you're actually correct, Scott, nice. On Windows, we could, for example, do a pipe or an ampersand, and we could check to see, hey, does this command, can we actually add other commands to our injection here? So what if I inject, for example, dir, and we ping ourselves 1 time and we inject dir? This is a blind injection, so there's no output of dir. So how can we determine if we're successful or not? Well, we could, for example, do a ping back to our attacker. So we do ampersand, ping back to our attacker, and we measure. Does that work? And all of a sudden, we don't just get 2 ICMP requests. We actually get 4, which is the built-in Windows 1. So we can see that, yes, we can actually append commands to our injection field here. But what command would you run to take over a Windows system? Like, on Linux, it's super easy. It would be netcat reverse shell, and we're done. It takes 5 seconds. But for Windows, where would we go? PowerShell, thank you. So we can see can we run PowerShell? Can we make PowerShell ping back to us and so on? And we would learn that, yes, we can actually run PowerShell here. So I'm gonna, from a cheat sheet here, I'm gonna copy over a little script that I'm gonna explain for you. So what we're gonna do is we're gonna ping our host, the local host, 1 time, just to keep things operating normally. Then we're gonna do an ampersand. Then we're gonna run PowerShell, no profile, non-interactive, execution policy bypass, and we're gonna run the following command. Which command? Please invoke expression, create me a new object, a web client. So this turns PowerShell into a web browser, more or less, like curl. Download the following script for me and invoke this script. This script is Parocat. Let me show you the source code of this. If I can click enter. So I just, in my command, I'm telling PowerShell, please fetch this file off the internet and run this file. This is created by Mick Douglas, one of the other SANS instructors. It is actually netcat. And once we have downloaded this file, we do, in PowerShell, we actually have a semicolon to determine other commands. Please run the following command, Parocat, connect back to 5650 on a port of your favorite number, and run cmd.exe. So we don't actually need this one. So this will actually potentially give us a reverse backdoor. So on our Linux here, instead of listening with tspeedup, why don't we do netcat listen verbosely on port 15088 and see if we can cause this system to call back. And all of a sudden, on Linux, we now have the Windows command prompt. So that's quite beautiful. We can now do, for example, we can go find maybe some config files that might have some sensitive information in it. We could now persist our malware, for example, like persist some malware to cause it to always call back to ourselves and so on. But the goal here was that, hey, to show you that when we are dealing with blind injections, we're not relying on the system to actually show us some information. We're just relying for some out-of-band channel to reveal us the answers. For example, such as a pingback or a domain name lookup, for example, or whatsoever. Should this server be allowed to connect back to things, by the way? No, the firewall, we say, hey, only allow port 84 for free most of the time. All right, so that's incoming rules. When do we define outbound rules? We should, but we seem to forget it. We still allow servers to actually go anywhere they want on the internet, and this caused this attack to actually work then. If we had outbound rules here, this attack would be thwarted. Now, there are many ways of finding such vulnerabilities like this, and I want to share with you a technique where we're actually using a fuzzing technique to discover vulnerabilities like these. So in my directory here, I have a script called collaborator merge, and I have a file called attacks.txt. This is basically a list of, how many do I have? 210 different attack vectors. And oh, wow, yes, you should. Here we go. So in my file here, thank you very much, we have an attacks.txt file containing 210 different attack vectors. And the different attack vectors, so this is just an example, but they're just these replace me values. So I want now to be able to send to a solution a bunch of different attack vectors, and I want to learn to see, does any of these attacks actually stick on the server, and if they're working or not. So with Burp Suite, I have something called the Burp Collaborator. So I actually need to look up here because my screen down here is bugged. I can create 210 different potential payloads that I want the solution to monitor for me. So I just created a bunch of different domains, 210 randomized domains that now belong to me. They're mine, courtesy of the Burp Suite project. So, and I will record any type of traffic, SMTP, HTTP, DNS, whatsoever, any traffic going to these Burp Collaborator domains, I will record. And what I want to do is that I want to intervene. I want to join them together with my attack payloads. So what I'll do is I'll bring up Notepad on the collaborators here. And I have this file here. And I'll just paste in my attacks here. So I should now have 210 attacks and 210 domains. And I'll call in my C:derived directory here, python.exe. I will call merge.py, and it will create me this join of these two files. So if you look at, for example, my attacks from previous year, I now have this unique domains in every single payload. Each payload now has a unique domain that we can call some kind of callback to. So say we want to fuzz a solution. We're not sure what we're looking for. We try every attack in the book. But every attack in the book has this unique callback to my own IP addresses and my own domains that I control. So say, for example, this payload here, this is the one that is working. So we receive some kind of HTTP interaction to this string here, xss.http. When we open this in our web browser, it just gives us a little random string coming back, which is fine. But when we open up the collaborator, and we click poll now, we can see that we actually receive a lot of different interaction towards this specific domain. So the domain up here says 6IPY. This one says 6IPY. I can now determine that, hey, my payload just caused a whole lot of DNS traffic and a whole lot of request traffic. And in fact, if we go in here, we can see that it's actually trying to fetch the different resources that I tried for. Here is this XSS HTTP call. So this is the technique that we're using to automate this and to scan thousands and thousands of scripts with different payloads and learning which payload caused which type of callback. This is also what the Burp Suite active scanning module, the vulnerability scanner, does for us in some cases. It's very, very useful. Now, there's going to be other vulnerabilities in this application, I'm sure. So going back to this one, we know we know that we can take over the system using this field here. But within a pen test, we cannot just stop there. We have to cover the entire attack surface. If not, we're doing the customer a disservice. So we should be testing more stuff. And we do have other stuff that is vulnerable here. I mean, it's running off the damn vulnerable web application, so go figure. There's, of course, going to be vulnerabilities here. And we have this user ID search here, where we can search for some kind of ID. And it says user exists. We can search maybe for 250. And it says user does not exist. All right, so we can determine if a user exists in the platform or not. By the way, have you ever seen hackers? They immediately, once they see a login field or some kind of input field, they try hack it without actually confirming how the actual functionality should work. I hate seeing that. When someone just tries breaking into a solution and they haven't really understood what should happen inside of the application. So what I'm looking at a binary condition where I have something existing or something that does not exist. And if you have say, for example, an SQL injection here, like, for example, I do a one tick, it still says user does not exist. It doesn't give us an error message. It doesn't show us something that is wrong. It just says, hey, this user one tick does not exist. So how do we confirm if there is a vulnerability here or not when we don't have any feedback from the application? This is actually what we're seeing the most in our pen test, that you don't have any feedback whatsoever. There is no stack trace, there is no error message. The application just replies as it would normally. And you're thinking there, oh, this must be safe then. There must be no vulnerabilities. What we could do is that we could inject, for example, a tick, and we could try to fix a query here. We could try to add something to our SQL. Most likely this system here has something like this. Select star from users where user ID equals, and then input from the user. So most likely it's something like this. Now we could inject, we are controlling this input here from the user. We could potentially try to inject something for this query to make it work. So for example, even for a user that does not exist, maybe our input would be 250. It says user does not exist. And then we do our input of tick, and maybe or 1 equals 1. So our input is actually going to be a tautology, an always true statement. Let's try this input and just see what happens. So user number 250 should not exist. But if I tell this query to be always true, the tautology, that user should actually return true if it does exist. So all of a sudden it says user exists. So we now can make us an idea that we actually have an injection here. What other things can we test? For example, what about and? Why don't we look for a user that does exist and try to focus our thoughts to see if we understand this properly. We're looking for user ID 1, and we're also saying that 1 equals 1 should be true because of the and keyword. This worked. What about 1 equals 2? And user does not exist. So we now have a solid understanding, I would say, of how our injection works. We can see definitely that we're inside of a query, and we can make some attacks work here. By the way, do you want to know how, most firewall vendors today, next generation firewall vendors today, they will look for this string here. So this tautology, this always true statement, forcing the solution to return something, they're looking for this. Do you want to know how to bypass it? So this is true, right? And all of a sudden, 50% of all the vendors, they're blind. Is this true? Is Chris Rocks equals Chris Rocks true? Thank you very much. But they're blind. They're just looking for a certain string in our inputs. And then we can add further obfuscation, like add some comments inside of here, or we can replace this with little pipe symbols. We can maybe break up the strings here with extra data. We can make it, for example, we can add anything we want in here. These are comments now, and SQL will still parse it as legitimate SQL. However, most vendors will actually be blind by this point. They need to normalize the queries to not be blind. All right, so we might have an injection point here, but we don't have any way to confirm or dump some data here. So to get data out of the database, there must be passwords inside of the database, right? There must be something else in here. How could we do that? Well, one thing we could do is try a union all. So we take a left side of the query, like this query up here. We take the left side and we join it with a new query on the right side. So we might be looking for example, user ID 1, and then we do union all, select something else. And we can comment out the rest of the query with this little semicolon hash here. So why don't we try this little input here? So we're looking for user 1, and it says user exists. We're still running a blind injection. But from here, we know now that, hey, this query on the right side is actually returning. In fact, if we add this to be 250, which should not exist in the database, we can still see that the right side of the query actually returns something. And this is how we would now pivot. We would pivot into the information schema database, and we would start looking at which tables exist, and we would go string by string. But because we are in a blind injection, this is better suited for automated tools, such as SQL map and other things. So instead of going for the whole union here, let me instead do a different example where we do the version number of MySQL and see if we can fetch this from the database. So what we'll do is we'll do a little and. So user should not exist. Actually, let's do should exist. And the version number of MySQL should be equal to something. But what's something? Like, I could, of course, guess different strings, different type of versions, and so on. And maybe if I'm correct, like maybe if I type in like a string here, 4.12, for example, I would get a true. Yes, user exists in the database. But I'm not very prone of guessing. So instead, I will use the substring function of MySQL. And I will tell the substring function, first of all, how do I know that this function exists in MySQL? RTFM. I read the fine manual, all right? And I know that, yes, there exists such a function. Now, in my substring function, I want this function to take in the version number of MySQL and give me only the first letter of MySQL and check to see, hey, is this equal to, say, the string 4? And it says, user does not exist. So it's not MySQL version 4. What about 5? And it says user exists. So whenever I'm looking at the first character of the @that version field, I get a return of true when I query to see if it's equal to 5. This is where we need to automate things, because if we continue like this manually, we're going to spend the rest of our lives fetching out MD5 checksums and bcrypt hashes from the database. This will not work very fast. So why don't we automate it with burpsuit? So we'll capture the request, the working attack request here. So we have a 4 right now. I'll press Control-I, send it to the intruder, and we'll use a fuzzer to automate our attacks for us. Now, what we're looking at here is the URL encoding of our string. So it doesn't look like the one I inputted, but it's actually just the same thing. And we can see that here's a substring function. This is the parentheses open. This is the @ sign, then we have version, and then we have a comma, and we have the number 1. So we're checking the first character to see if it's equal to something. But we want to check every other character as well, not just the first character. So I will embed a little variable around this one tag. And then we have a comma, and then we have the length of the substring, which should be consistent. It should always be 1. We want to check one character at once per time. Then we have the rest of our query equals, and we have parentheses, and we have the number 4. Now, 4 did not exist, but I want to fuzz this field as well. So I want to go through every character from this @at version variable, and I will check to see, are they equal to a list of strings that I define? So first off, in my first variable, I'm going to specify a number. So numbers from, say, 1 to 6. Versions are not that long, but for a bigger field, I would maybe need to specify 32 in length here. So that's going to cause us to have, we need to define an attack here. This will cause us for going through the numbers 1 to 6. And in the second payload, which is this one over here, the number 4 currently, I want to define which characters do I want to check for. So if this was, for example, an MD5 hash I wanted to check, this would be hex characters, 0 to 9, 8 to F. But because we're in a version here, I'm actually going to use the numbers 1, 2, 3, 4, 5, 6, 7, for example, and then dot and a dash. Dot and a dash. And we go start attack. So is this multi-threaded, by the way? Yes, it is. So what we're looking at here is that the solution is now in the first payload, it's trying the different characters, so which position of the character we want to check is equal to the payload of 1. And then we're checking to see, is anyone equal to the number of 2, 3, 4, and so on for every single character. Now, this will only cause us to have 54 requests, so it will take a little time. But if you consider this to be for an entire database, maybe we're dumping an entire database this way, this could take potentially a very long time. This could be very time-consuming, and so on. Another nice thing to mention is that in our attack here, we're using substring, the substring function. Now, this substring function is nice when we have like a binary output. But in many cases of blind injections, we don't actually have any output at all. We don't have like a binary yes or binary no. We just have a consistent output always. For those times, we normally add cost to our query. So instead of saying and substring equals, for example, the value of 5, like we just did, instead of saying this, we do and benchmark something. For example, benchmark the MD5 function 10 million times if the substring is 5, for example. And then we measure it by time. We go saying, hey, if this query works, if the substring is 5, like this is pseudocode, so it won't actually run. But if the return is 5, well, then benchmark this function 10 million times, and that will take 2 seconds. Hence, we know now that this exists. So in our database here, first of all, it might be hard to read if this actually works or not. So in our options here, I want to add something. I want to do a little grep extract. So I'm going to go here and select in my response when the user does not exist or when it exists. I want to have this output in my results table. And now I can sort by this results table, and I can go and say, hey, show me only the queries where the user exists. Actually, this should do. These are different than where the user does not exist. Well, because the query worked. So I can now copy these. I can bring them into Excel, our trusty old friend Excel, right? And I just simply paste. I do data, I do sort, and I can sort on column number 2, which is the position of the characters I'm testing. And it looks to me that the version of MySQL is version 5.5.32. Are we correct? Well, only one way to find out. We cheat. We open up the database, and we can see that the database version is actually 5.5.32. So I know I'm holding up everyone for lunch. I really don't like that. I want you guys to have a great lunch, and thank you for listening to me. Hopefully it was insightful, and hopefully it was a break from all the PowerPoints.
We do have time for questions because lunch is not quite ready yet. Anyone?
I know it's a bit scary, but if you want, you can ask in Norwegian. But yeah, blind injections, this is what we're seeing. So, question? Yeah. Tricks for establishing the vendor. Well, you could maybe try different like built-in variables to see if any of them work or not. You can check to see, for example, the existence of either the master database, for example, or the information schema database by trying to pivot union all into databases that should exist if the database is a certain version. You can also see how they parse and understand data types. So, for example, SQL Server will be very strict in how it accepts different data types, but MySQL is very forgiving. So we don't like MySQL because it's very forgiving. Let's run with Postgres or something else instead. For those who couldn't hear, by the way, the question was how could we determine what type of backend database we're running? And most of the time it's just by trying and failing. My best advice is actually to run SQL map against the system, and it has some fantastic algorithms to try to determine this for you. And this is from where we left off now. This is where we normally run. This is where we actually use SQL map to help us exfiltrate information, because now we have a solid understanding of the vulnerability, and we can then use it to use SQL map to automate things for us better. If this was not blind injection, by the way, let's take a look at what happens then. Let's do a little or 1 equals 1 when the vulnerability is not blind. This is what we see. We get a dump of all the tables in the database. So, of course, once you're blind, which is happening in most cases, you don't get this output. You either have just a binary output, or you just have to use time to your advantage. Any other questions? Yeah.
The attacks you show, if I understand correctly, are based on injection.
Right.
How common is that applications are still not protected from injection, in your experience?
I mean, so the alternative would be that developers are actually smart. That they're actually doing their job correctly, and maybe even the frameworks are actually not allowing you to do mistakes, and they would be written securely. And you would have to be smart to do something stupid. That would be a dream world. But yeah, we're seeing it all the time, unfortunately. But not externally. Once you have one foot inside, that's when the vulnerabilities normally arise. And also with introducing new technology that we don't understand, such as microservices. I mean, I was mind blown by everything I did not understand from the previous talk. I was like, wow, I don't know microservices. But by introducing such systems, we very often introduce misconfigurations, developers putting scripts online that should not be online, signing scripts and so on that they thought were hidden or they thought were not exposed. And we have new classes of vulnerabilities. Yeah. So no SQL injection type of thing. Well, this is where Alan brilliantly explain. But if I have some examples, yes, you're more likely to be injecting JavaScript instead of injecting actually structured query language injections. So for those type of things, so we're normally doing fuzzing here when we're trying to identify these things. We don't always know that. We don't necessarily know exactly what we're looking for. So we're just trying every single thing in the book, and then we measure to see any time we have a discrepancy, something different than normal, that's when we investigate. And if I can see, for example, in my fuzzing activities, whenever I'm injecting NoSQL type of commands and injection scripts, I can see that the application seems to behave differently. This is when I go digging and I go investigating to see if I can make it stick or not. But it's very important to know that the attackers doesn't necessarily know what type of vulnerability they're looking for. So they're just grasping on some kind of difference from a normal results to a legit result. In our case here, for example, the difference could be, for example, whenever you have an error message, you're actually being redirected to the front page. And that's the entire thing you will use for the rest of the exploit to determine if it's working or not. All right? Anyone coming for beers later? This is why I'm here. Free beers, right? Is it free? No. Oh, that's... I guess I'm heading back then.
Unfortunately, we don't have a curry sponsor, so you have to pay for your own beer later, but I hope you'll join anyway. The rest of the company is pretty cheap, right?
I mean, it's Oslo. You can't have free beers in Oslo, can you?
Show me the free beer in Belgium.
Oh, free beers in Bergen, yeah. Next time, huh? Question of them top? Dynamic collaborate injection? Dynamic library injection, so DLL injection? So that's something that we use post-exploitation after the fact that we've gotten some access to a server and inject ourselves into existing processes such as Explorer and so on. But from here, I've never had a thought even to try to inject some DLLs. I don't think so, no. Like, would you run DLL injection through the web app from here? With PowerShell, we can do anything. So yeah, definitely it would be theoretically doable, but I'm a fan of reverse shells and just get that payload running and get me some command line action. And then I would consider doing DLL injection. For example, getting my stager to run some kind of extra, like maybe some kind of command and control stuff to allow us to pivot and run hashes, hash dumps, and steal passwords and so on from the systems. I hear, brother. Yep. All right. Is it safe to bring in my hand luggage?
Yes, it's coffee and chocolate. So
nice. Because one time I got a baseball bat, I'm like, what am I going to do with this, right? Thank you very much.